Okay. So today we are going to do the transfer functions of electrical circuits. And before we dive into any question, I'd like for you to know these basics. So the first one is you have passive components in the circuit. You have a resistor, which is a passive component. And then you have an inductor. And then you have a capacitor. Now, if you want to find the voltage across this particular resistor, is going to be, let's say, Vm sub R to indicate that is the voltage across the this particular resistor of T is equal to I of T multiplied by the value of the resistance R. And then the Laplace equivalent of it, if I'm to find the Laplace of this particular function here, this is going to be VRS I of S and then R, right? You all like agree with me. Now, if I'm to do the same thing to this particular inductor here, and I'm to find the voltage across this inductor, I could say that the voltage across this inductor of T is equal to L d I of T dt. And if I'm to find the Laplace of this particular equation here, is going to be VL of S is equal to L, and then the Laplace of any derivative, since this one is a first derivative, then it's going to be just multiplied by S, and then I of S. That's all. Now let's come to the capacitor. Capacitor C, and then I want to find the voltage or the voltage function of it. But before I find the voltage function, we are all used to the fact that I of T is equal to C d Vc of T over with dt, right? If I want to do some manipulation or like some manipulations on this change of subject, I'll find that the voltage across this is 1 over C, then the integration of I of T dt from a particular time of 0 to, let's say, particular time T. Now, if I find the Laplace of this particular function, I'm going to get this. Laplace of this gives me Vc of S is equal to 1 over C is a constant, so it doesn't change. And then the Laplace of an integral is going to be I of S over S, right? So I can rewrite this as, so you are seeing that for this particular voltage, this amount of current passes through it when you have this amount of, let's say, resistance. Likewise, you can see that if you have a particular voltage across an inductor, for this amount of current to pass through, you have to get this particular impedance. In this case, it's an inductive reactance, right? And then for the capacitor for you to get this amount of current to flow through, you have to get this amount of impedance, this 1 over C times S. So let me write this well. And then S. So we can see that if you want to represent these particular passive components in a S domain, then it's going to be this in a Laplace domain is still R. Nothing changes. But for an inductor, when you convert it into a Laplace domain, then it has an impedance of SL or LS, like either way that you choose it. And then for a capacitor, it has an impedance of 1 over SC, right? So that's what we are going to use. So just keep this in your head, and everything will be simple for you from now on. So the next thing that I want to talk about is the um, matrix, right? So for the matrix, depending on which rule that you want to use, if it's the mesh analysis or the nodal analysis or something, if it's the mesh analysis, you count the number of meshes in there. If you have two meshes, then your matrix is going to be a 2 by 2 matrix, right? Let me write so I think it's crooked. A 2 by 2 matrix. So we have the first column, the second column, and then the first row and the second row. And this particular index here is every impedance that is in the first mesh. So let's say 1, 1 is every impedance that's in the first mesh. And then this particular position here, 2, 2, is every impedance that is in the second mesh. Now, this particular position 1 and 2 is every impedance that is both in the first mesh and then the second mesh. And then here, 2, 1 is going to be the same as this. So position index 1, 2 is the same as position index 2, 1. So whatever that you find here is the same as here, right? Likewise, to if it's a 3 by 3 matrix, you have one first column, second column, third column, first row, second row, third row. Position index 1, 1 is going to be every impedance present in a mesh 1. Position index 2, 2 is going to be every impedance present in a mesh 2. Position index 3, 3 is going to be every impedance present in a mesh 3. And then position index 1, 2 is going to be every impedance present in the mesh 1 and then mesh 2. And then position index 1, 3 is going to be every impedance present in the mesh 1 and 2. Likewise, to position index 2, 1 is going to be the same value in the position index 1, 2. And then position index 3, 1 is going to be the same value in the position of index 1, 3. Now to find these positions, it's going to be 2, 3. It's going to be the impedances in the present in both the mesh 2 and mesh 3. And then the position index 3, 2 here is going to be the same as the position index 2, 3. So if you are being given a 4 by 4 matrix, you should know how to do your own thing. Let's say a particular circuit has 4 meshes. You should know how to do the matrix. So let me explain with an example. Let's take the first example. So let's say you have this question, and then you are being asked to find the transfer function. You are being asked to find the transfer function. And then from what Dr. Poku said in class, he said, don't confuse with the input and output. The input is what you are sending into the system, and then the output is the thing that you are trying to measure. In this case, you are trying to measure the voltage across this inductor here. That is our output. So to find the transfer function, let's say J of S is going to be this over that. This is our transfer function. Now, let's convert this circuit into the S domain. If we do that, it's going to give us something. It's going to give us this. Now, from what you've done above, the V of T is V of S. Then your inductor of inductance, 2 ohms, becomes 2 multiplied by S. And then your resistance stays the same, right? And then your resistance here to stays the same. And then this thing here to just multiply it by 2. Now you could use nodal analysis or mesh. But me, I'm used to the mesh, so I'm going to go with the mesh. So if I'm to do it with the mesh, you can also try with the nodal analysis and see if you can arrive at the same answer. So there's the first mesh here, I1 of S. There's a second mesh, I2 of S. Now I have 2 meshes here, right? So it means that I'm to get 2 by 2 matrix. Now, mind you, the output function is right here, right? So let's forget about that for now. So if I'm to form my 2 by 2 matrix, the position 1, 1, right? So let me do the whole thing. I have column 1, column 2, row 1, row 2. The position index 1, 1 here should have all the impedances present in the first mesh, right here. So all the impedances present here is this 2s and then the 2. So I sum them up. 2s plus 2, right? And then the position index 2, 2 here should have all the impedances present in the second mesh here. So all the impedances present here, I see 2, 2, and 2s. So it's going to be 2 plus 2 plus 2s. And then the position index 1 and 2 here is the impedance present in both the first mesh and then the second mesh. And then the impedance present in here, both in the first mesh and then the second mesh, is this 2 right here. Now, mind you, we have to negate it. Always, we have to negate it. So since the value in the position index here is always the same as that here, then it means that here too is -2, right? So this is how to form the matrix. And if you don't get it, you can go back, pause it, and then re-watch it again. And if you do get it, we are even going to solve a 3 by 3 matrix soon next time. Now, this matrix represents impedances, right? So I have to do it in such a way that when I multiply the impedance with the current, I have to get voltage, right? So the first one here is the current here, I1 of S, and the current here is I2 of S, right? And then for the voltage is V of S and 0. Now don't go and write this particular place is not VL of S. Most students actually do that. Instead of writing this, then you see them writing this. It's not supposed to be that way, and I'll tell you why. Because this one is a passive component. We are just trying to take the voltage across it. But this is an active component, so we do take it. Imagine if the a voltage source is connected here. Let's say V2 of T. That's where this one to become V2 of S. But here lies the case where a voltage source is connected here. So this mesh has 0 voltage sources, and this mesh has 1 voltage source. That's why we consider this part to be 0. And to easily remember this too, just like remember this this is the V is equal to your I and then your R, right? Or this, according to Ohm's law, right? So it helps you, like remember where you have to put your I1 and then your I1 and I2 and then your V of S and 0, right? So that I don't easily get confused. Now, the next concept here is how then do we find the transfer function? How then do we find the transfer function? Okay, so we are trying to find V of S. We are trying to find VL of S over V of S, right? Then it means that if we want to do anything, we have to multiply the I2 of S by this impedance here to get VL of T or VL of S here. So the first course of action is VL of S is equal to I2 of S multiplied by 2 of S. So it means that we have to find the I2 of S. And then the I2 of S is here. Now, there are several ways you could use to find your I2 of S that you are looking for. But I'd advise you to use the Cramer's rule. The Cramer's rule is simple, right? So the Cramer's rule says that if you want to find a particular variable, right? So you take that variable. So in this case, you are trying to find I2 of S. So I2 of S, right? You take this, right? So this is, let's say, column 1 and then column 2, right? If you want to find I2 of S, you take this and then you put it here in the column here. Likewise, if you want to find I1 of S, you take this one, right, and then you place it here. Okay, so we just let me show you what I'm trying to say. So this, since I'm trying to find I2, then I have to go to the second column. I write this already there, right? Then I replace it with this one. I get V of S and then 0. And then I divide it with the normal matrix here, which is 2S plus 2 minus 2 minus 2, 4 plus S. That's how the whole thing is. And if I want to find I1 to I1 of S, I take this one always. Then I replace it or I put it at the first column here. I get V of S 0 minus 2, 4 plus 2S all over. Then the denominator always remains the same. 2 minus 2 minus 2, 4 plus S, right? But we are looking for I2, and I have to find the determinant of it, determinant of all of them. Okay. Now, for the determinant, let's see the determinant of the numerator, right? I don't want to write the whole thing. It's going to be 2S plus 2 multiplied by 0 minus 2 times V of S. And it gives me 2 times V of S. And then the determinant of the denominator, which is this, is going to be 2S plus 2 multiplied by 4 plus S minus 2 minus 2. And I expand. I get 8s plus 2s squared plus 8 plus 2s minus 4. I group like terms. 2s plus 10s plus 4. Now to find I2 of s, it becomes simple for me, right? It's just the determinant of this right here, which is this 2v of s, all over the determinant of this right here, which is 2s squared plus 10s plus 4. Now, based on what we've already done so far, what we've written right here, that VL of S is equal to I2 of S times 2. I can make some substitution here, right? So I can see that can imply that I2 of S is the same as VL of S over 2S, which is the same as 2V of S over 2S squared plus 10S plus 4. Right? Then in that way, then it's looking like what the person wants me to find, right? So the transfer function therefore becomes VL of S. Let me put this down. Okay. When you do your substitution, you get to see that V of S is equal to 2 times 2S all over 2S squared plus 10S plus 4. And it gives you 4S all over 2S plus 10S plus 4. Now, surely you can break it down. 2S squared plus 5S plus 2. Then this your transfer function. So from the question, we've seen that our transfer function VL of S over VS is 2S over square plus 5S plus this, right? So we've solved the question. And if the input is a step function, you know how to go about it. If it's a ramp, you know how to go about it. It's a parabolic function, you know how to go about it. So from the electrical circuit, the transfer function VL over V of S is the 2S over S squared plus 5S plus 2. Great. Let's move on to the next one and let's see if we understand. So the next one, this is it. You have to convert the circuit into its Laplace equivalent. And then to do that, it's going to be your, let me change. Your V of T is going to change to V of S. And then your resistance is also the same thing, just the same thing, 1. Then the resistance here too is the same thing, 1. But then your your inductor here, when you convert into the Laplace transform to find its impedance, it's going to be 1 times S. So it's just S. Likewise with the side, and likewise with the one here. So if we should draw it all over again, we'll get here S1. this V of S, this S, and that's S. And we've been asked to find VL of S. So this has three meshes, right? The first mesh is here, I1 of S. The second mesh is here, I2 of S. And the third mesh is here, I3 of S. So this should tell me that I'm going to get a 3 by 3 matrix. So first of all, I have to get my 3 by 3 matrix of impedances. So the first part is going to be all the impedances in the mesh 1, right? So it's 1 and S. So I sum them up. So the impedances present in this first mesh here is the 1 here and then the S here. So you sum them up to get 1 plus S, right? And then the position index 2, 2 here too means that all the impedances in the second mesh, and then the second mesh is right here, right? And then all the impedances present there are S1 and S. You can see it here, you can watch it. S1 and S. So I can sum them up and see I have S plus S plus 1, right? And then the position index 3, 3, if I'm to find the impedances there, is going to be the summation of all the impedances in the third mesh, which is 1, 1, and then the S there. I do know if okay, which is 1, 1, and then the S here. So it's going to give me 1 plus 1 plus S. Let me close. Great. Now, here is a position index 1 and 2. It means that all the impedances present both in the first mesh and then the second mesh. So the first mesh is here, and then the second mesh is here. And then the impedance present in these two meshes is the S. So just S. Now I have to negate it, minus S. And since the position index 1, 2 here is the same as the position index 2, 1 here, it means that the value present here should be minus S. Now let's go to the position index 1 and 3. It means that all the impedances present in both in mesh 1 and then mesh 3. And that is the 1 here. 1 here. So it's going to be minus 1. Right? And since position index 1, 3 is always the same as 3, 1, here so it's going to be minus 1. Now let's go to the position index 2 and 3 right here. It means that all the impedances present in both mesh 2 and mesh 1, and that is here and here. And the impedance present is just the 1 here. So I negate it and I negate that. Right. So now we've gotten our matrix. Let's simplify the whole thing. 1 plus S, S plus S to S2, S plus 1. Then you have 2 plus S. Here is minus S, minus S, minus 1, minus 1, and minus 1, minus 1. And there you have it. So always have this in mind. V is equal to I, Z, right? So it means that my impedance matrix, which is this, 1 plus S, 2S plus 1, S plus 2, minus S, minus S, minus 1, minus 1, minus 1, minus 1, multiplied by the current is equal to Now let's take our time here. Let's move back to the diagram and see. There's the first mesh, right? The first mesh has an active voltage source of this, but the second mesh and then the third mesh don't have. So you can see that this side is V of S and 0, 0. Now we have to find VL of S over V of S to find the transfer function. Now to find VL of S here is going to be that VL of S is equal to the current I2 of S times the S, right? So I2 of S times the S. Let's call this one equation 1. Now the equation 2, to find the equation 2, that's where Cramer's rule comes in. So we want to find I2 of S. Right? So for I2 of S, according to Kramer, it's supposed to be I2 of S all over the determinant of, since we are finding I2, then we have to replace this position, this column here with this right here. Since we are finding I2, we have to replace this column right here with this. So we get 1 plus S minus S minus 1, and then we replace it with what we have over here. And then we continue it in that way. All over this matrix. 1 plus S minus S minus 1 minus S 2S plus 1 minus 1 minus 1 minus 1 S plus 2. Find the determinant. Okay, so to find the determinant of the numerator, now you can use the plus, minus, plus thing. Yes, fine. It actually goes fine with you. So what that says is I have to take plus, 1 plus S. I take this side right here. Then I find the determinant of 0 minus 1, 0, S plus 2. Right? So the trick here is just to find this part. Start with the plus here. Multiply it with the 1 plus S. And then you exempt all the rows and columns. And then you find the determinant of what's remaining. And then you multiply it with it. So we'll do it for the second column too. So this side is going to be minus V of S multiplied by the determinant of minus S minus 1 minus 1 S plus 2. Right? Because we have taken this whole part and this whole part out. What is left with is minus S here, minus 1 here, and then minus 1 and S plus 2. And then we'll go with plus multiplied by minus 1 multiplied by the determinant of, you take this one out, you take that one out, you are left with minus S, 0, minus 1, and 0. So you have minus S, 0, minus 1, 0. Find the determinant of that. So when you solve it, you are going to get 1 plus S, 0 multiplied by 0, that's 0. 0 times S plus 2 minus 1 multiplied by 0 and minus V of S. You do the same thing here. Minus 1 minus 1 minus 1. This gives you 0 minus 0. One plus s. This whole thing here gives you 0. 0 minus 0. You have v of s multiplied by minus s squared minus 2s minus 1. And you have 0 here. So you are being left with v of s multiplied by s squared plus 2s plus 1. There's the determinant of the numerator. Now let's go to the determinant of the denominator. We are going to go with the same thing. You have plus, minus, and plus here. So it's going to be the determinant of the denominator is going to be plus 1 plus s multiplied by the determinant of, we are getting rid of this side, and this is what's left. Okay. So we have 1 plus 2s minus 1 minus 1, 2 plus s. I'm sure you can generate this on your own by now. So let me just quickly run through and now if you want to multiply through, you get that's you are finding the determinant of this. So it's going to be 1 plus s. This multiplied by that gives me 1 plus 2s, 2 plus s, and then minus 1 here. Then this right here, I get minus times minus gives me plus, right? And you get s multiplied by this times this minus s, 2 plus s minus 1. Minus 1 times minus 1 is positive 1. And then plus times minus 1 gives you minus 1 multiplied by minus s times minus 1 gives you s multiplied by minus 1 times 1 plus 2s. Okay. If you expand, or when you expand, I don't know why I say if, when you expand, you get 2 plus s plus 4s plus s squared minus 1. That's for the first one. Then the second one is going to be minus 2s minus s squared minus 1. And then the third one is going to be s plus 1 plus 2s. Now, the reason why I'm doing it this way is that I don't want to do it the horizontal way. And then sometimes it confuses students a lot when you have to do like heavy calculations like this. So the 2s plus s gives you 3s. Let's continue. If you expand this and that, you are going to get 2s squared plus 5s plus 1 plus 2s cubed plus 5s cubed plus s. And if you expand this one to, you are going to get, okay, let me take minus 2s squared minus s cubed minus s. And then when you expand this one to, you get minus 3s minus 1. Because this s and this s gives you 3. Now, I don't want to do it the horizontal way because I feel like it will confuse me a lot. So for me to easily like remember what I'm doing, I first of all arrange them, right? So I have 2s cubed here, 2s cubed. Then the next one is s squared. I have 2s squared and then 5s squared here. That gives me 7s squared. Then the next one is s, 1s, and then 5s. That gives me 6s. And finally, the plus 1. And then this side right here, I, like arrange it again. I get minus s cubed minus 2s squared minus s, right? And then the third one is minus 3s minus 1. See, that when I do it this way, it's easy for me to sum them up, right? And I'll get the same thing too. So 2s cubed minus 2s cubed is s cubed plus 7s squared minus 2s squared is plus 5s squared. And then plus 6s minus s minus 3s, that's 2s. And then this one sums up to 0. So then I get the determinant of the denominator to be this. So the whole thing, I2 of s, is going to be the determinant of the numerator over the determinant of the denominator. And from what you've done so far, the determinant of the numerator is the v of s is this one. Right, so let me scroll up for you to see. So, okay, it's v of s squared plus 2s plus 1. Okay, so v of s squared plus 2s plus 1 over s cubed plus 5s squared plus 2s. But that's not it. So this one becomes my equation 2. So to find equation 2 is here. VL of s is equal to I2 of s times s. Let me write it down. Equal to I2 of s times s. This is my equation 2. So equation 2. Equation 1, sorry. So I have to substitute, I have to make I2 of s the subject here, and then substitute it here. When I do that, I'm going to get VL of s over s is equal to V of s multiplied by s squared plus 2s plus 1 all over s cubed plus 5s squared plus 2s. When I change this, I get VL of s over V of s gives me s squared plus 2s plus 1 all over s cubed plus 5s squared plus 2s. I can factorize s here, right? I'll get s over s squared plus 2s plus 1. And then s squared plus 5s plus 2. And this cancels this right here. And this is my transfer function. Right there. Okay. So I'm going to let you try some. You can find the transfer function of this. Find the transfer function of this. Or you can try it out with your friends, or you can just try it out by yourself. And if you do find it, you can draw by the series of this, and then we'll discuss it. I'm not going to write the answer here, but you just do it like in a group setting, blah, blah, blah. And then this is for a 2 by 2 matrix, right? So for a 3 by 3 matrix, you can also try this one too on your own. You can find a transfer function by transfer function. Now, the next electrical circuit that we'll talk about is the op-amps, right? I know you already know this, that an op-amp, you have two types. You have the inverting and the non-inverting. So before I speak about the op-amps, let's quickly revise to the inverting one is when the input voltage is being applied to the negative terminal. And then you have a particular impedance. Impedance here, and a voltage VI is being applied here. This is Z2. And then for the feedback part, this is Z2, and this is connected to ground. So to find the transfer function, find the transfer function of this, then the inverting op-amp is going to be minus the feedback impedance over the input, the impedance here, Z1. That's the transfer function. And for a non-inverting op-amp, you have the input voltage is being applied to the positive side of it, Z1, VI, and then this one is being reset, it's being grounded, and you have it V2, and then the output. So to find the transfer function of a non-inverting op-amp, it's going to be V output and the input, and 1 plus Z2 by Z1 is minus. Let me cross check. Feeding you. Yes, plus. Okay, it's plus. Wait. So let's go ahead and pick a question. Now, from what I've done so far, you can see that this gives me the Z2, and this gives me the Z1, right? So I can first of all have to know, so this is an inverting op-amp because the voltage is being applied to the negative terminal. So V2 is equal to, and I convert this one to the Laplace, the 100K to the Laplace. It's still the same thing, doesn't change. So 100K. and then plus there's a capacitor. And when you want to, when it's being converted into the Laplace impedance is 1 over 2 times 10 raised to the power minus 6 S, because it's 1 over SC. Don't actually forget this. So you get plus 1 over 2 times 10 raised to the power minus S minus 6x, 6s. And then the Z12, it follows the same pattern, 500 times 10 raised to the power 3 plus 1 over 2 times 10 raised to the power minus 6 S. So according to what we found, the OPAM V of S over Vi of S is therefore equal to minus 100 times 10 raised to the power 3 plus 1 over 2 times 10 raised to the power 6 S, all divided by 500 times 10 raised to the power plus 1 over 2. You might be tempted to leave your answer this way, but if the question asks of you to find the number of poles, you can't leave it this way. So you have to find a way to, dump it down in such a way that if the next question that follows says that you should find the number of poles, you wouldn't suffer. So what I'll do here is that I want to make the S not a denominator, right? So I first of all have to multiply the both part of the fraction by S. So this is sort of a create and destroy thing. So I create the S here, then I destroy it here. Such that when the S cancels the S, I still get the same thing, right? Now I still want to keep this fraction clean, right? I don't want anything at the bottom here. So I don't want to see 2 times 10 to the power minus 6. I don't want to see anything like that. So I create it and then I destroy it. Right? When I do that, when I multiply through this whole thing by this whole thing, right? So I get 100 times 10 is the power 3 times S times 2 times 10 is the power minus 6 plus this S here cancels the S here. And this 2 times 10 is the power minus 6 cancels the 2 times 10 is the power minus 6 here. So I have 1. For the denominator, I have 500 times 10 is the power 3 times S times 2 times 10 is the power minus 6 plus the S here cancels the S here. The 2 times 10 is the power minus 6 cancels the 2 times 10 is the power minus 6. And I get to 1. Now I can go ahead and further simplify. When I multiply this, so there's a minus here. So minus this times this, you can put it on your calculator and it will give you 0.2 times the S plus 1 all over. When you punch this on your calculator, you get 1 times S plus 1. Now again, I want to leave some things too clean, so I can't just leave it like this. I want to, clear out everything. So 0.2 can be written as 1 over 5 multiplied by S. Now you can leave your solution to be like this. Like it's up onto you. You can still find the number of poles here, and then the zero is up onto you. But I'm just trying to, simplify my own thing. So I can factorize the 1 over 5 out, right? Then I'll get 1 over 5 s plus 5 all over s plus 1. And then I get 1 over 5 s plus 5 all over s plus 1. So there's a transfer function. You can decide to stop here. If you're adventurous, you can go ahead and then try and get this. So it's always the same thing. So you can see that it's simple for me to find the number of poles here and then the zeros should the question ask me. Because I'm sure he can bring a diagram like this and then it will have babies there. So you find the transfer function, right? And then you find the poles and blah blah blah. And it all goes that way. And yeah, that's how the whole thing is. Let's go to the next one. This is a non-inverting amplifier. It's evident because the input voltage is being applied to the positive terminal of the op-amp. Now, if you've not still seen it yet, this right here is our Z2. And this right here is our Z1. So the transfer function of a non-inverting op-amp is going to be like what we said, 1 plus Z2 over Z1. Right? Okay, wait. So the transfer function V of S over Vi of S is going to be 1 plus the Z2. The Z2 is going to be the sum of this and that. When you convert this 110 kilo ohm into its Laplace transform, since it's a resistor, it actually doesn't have any effect. It's the same thing. So you are going to get 110 times 10 is the power 3 plus they are in series. But for the capacitor, the Laplace impedance of it is 1 over SC, where the C here is the value of the capacitance here. So you get 1 over 4 times 10 with the power minus 6 and S all over the Z1. The Z1 is here. We do the same thing now we did at this side. We get the 400 times 10 with the power 3. Then we add it to the inverse of 4 times 10 with the power minus 6 S. So it's the same thing here. Now, I know most people get confused around here. They don't know how to, go about this whole thing. Let me just make things. If you have 1 plus A plus B, right? It's the same as saying that the one there is B over B plus A over B. Now, since the denominators are the same, I can say it's B plus A all over B, right? So I first of all said B over B is the same as 1, so I've changed nothing there. Then I made the denominators the same. Then I'm able to do them like this. So I can do the same thing to the side. I can see that I have 400 10 is the power 3 plus 1 over 4 times 10 is the power minus 6s all over 400 times 10 to the power 3 plus 1 over 4 times 10 to the power minus 6s. This thing is the same as the one I've written here. So when you cancel this and this, it gives you the 1. Then I write it here. Then I continue by writing 110 times 10 to the power 3 plus 1 over 4 times 10 to the power minus 6s. Then 400 times 10 to the power 3 plus 1 over 4 times 10 to the power minus 6s. Now I can just, since the denominators are the same, I don't have to do any complex calculations. I can just add this side and I add this side, right? So I can continue by writing is equal to 400 times 10 to the power 3 plus 1 over 4 times 10 to the power minus 6s plus 110 times 10 to the power 3 and I can divide all by this thing. This s. Then I the 400 plus this one, then I sum them up. When I do sum them up, what do I even get? Okay. The 400 plus the 110 here gives me 510 times 10 to the power 3. And then this is the same as this thing here, right? It's like adding x plus x to give you 2x, right? They are all like terms. So I could just say 2 over 4 times 10 to the power minus 6x all over 400 times 10 to the power 3 plus 1 over 4 times 10 to the power minus 6s. This cancels it to be 2. So I could do the same thing that I did above. I don't want to, have s below. Like I want to do it in such a way that if I'm asked to find the transfer function, it's very simple for me. The poles of the system or the zeros of the system. So 510 times 10 to the power 3 plus 1 over 2 times 10 to the power minus 6x all over 400 times 10 to the power 3 plus 1 over 4 times 10 to the power minus 6x. Now, I can create and destroy, right? So, I don't want to have 6 at the denominator. I don't want to have the s at the denominator, right? So I can create and then destroy. So I'll create the s here. And I'll create another s here. Then to destroy the s that I've already created. So that when I multiply the s2, I'm actually getting rid of the s here at the denominator. Then I'm bringing it as a numerator here. And then I don't want to also have 4 times something, like I don't want to have these as my denominator. So I have to create something and destroy something, right? So I could multiply here. I'll create the 4 times 10 to the power minus 6. And then I'll destroy it here. Now I hope you are wondering why not multiply through by the 2. If I do multiply through by the 2, we'll still get a fraction of 1 over 2 times 10 to the power minus 6 here. So it's better to multiply through by the 4 times 10 to the power minus 6 here. Okay. So if I do what I did, if I go through with it, I'll get, let me take the calculator. Okay. So 5 times 10 to the power 3. 510 times 10 to the power minus times 3 multiplied by the s times 4 times 10 to the power minus 6 plus this, the s here cancels the s here. The 10 raised to the power minus 6 here cancels the 10 raised to the power minus 6 here. The 2 goes inside the 4 2 times. Then I have 2. And I do the same thing to the denominator too. I multiply 400 by 10 raised to the power 3 times s times 4 times 10 raised to the power minus 6 plus the s here cancels the s here. The 4 times 10 raised to the power minus 6 cancels the 4 times 10 raised to the power minus 6. And I get 1. Okay. If I should multiply this 510, this gives me, if my calculations are right, I get 2.04 s plus 2 all over. I do the same thing to 400 times 10 to the power 3 times 4 times 10 to the power minus 6. I get 1.6 s plus 1. I can do the same thing that I did in a previous question to actually simplify your stuff, but I don't think I have the heart to do it. So I'll leave it here. I can still find my transfer function here. It's actually not that hard. Yeah. But then maybe you can, make s. So I'll just factorize the 2 over this one here. I'll get it to be 2 over 0 4 1.6 s plus 1 over 1.6. Then we just solve it and see what we got. This is 1.275 s plus 1 over 1.04. And then s plus 1 over 1.6. So it becomes easy for you to find the zeros and the poles of the function. Right? So I'm going to leave some for you to try. I don't want to try it all. So you can find the transfer function. Transfer function for you and your friends to solve. Transfer function T of S is equal to V S and VI of S. And then the next one you can find the transfer function. To find transfer function. Okay. Transfer function. Okay. J is equal to V of S all about O. Yeah, so you can find it and maybe you and your friends can try it out and compare answers and teach yourself to. So in the next video, I'll be going to the mechanical systems, how to find the transfer functions of the mechanical systems. So I'll see you then.